Alright, homework 3, problem number 1. Prove the cardinality of any finite set is different than the cardinality of its power set. Now, what we know is that the cardinality of the power set is going to be equal to 2 to the exponent of the cardinality of the set itself. So the set here is going to be called A. This is going to be an example set A. And the definition of a power set is simply every possible subset that you can make out of this set right here. So for example, we have 1, 2, 3. We have 1, 2, 1, 3, 2, 3, 1, 2, and 3. And then we have the empty set. And some people will write that one in first. It doesn't really matter. The order here doesn't matter. All that matters is that contained within our set, we have every possible subset. 1, 2, 3, 4, 5, 6, 7, 8. Note that the cardinality of this set here is 1, 2, 3 because we have 3 different elements in it. So therefore, we expect the cardinality of the power set to be 2 to the third power based on our definition right here. And you can see that we have 1, 2, 3, 4, 5, 6, 7, 8. The cardinality of our power set is 8, which is what we expected. But definitions are really important here, so let's remind ourselves that this is a subset of A if and only if for every single item in here, that item is also found in A. That is the definition of a subset. And by definition, the power set is every possible subset. So for example, by the definition of subset, when we look at this set right here, we have 1, 2, 3. And we ask ourselves, is every single item in here also found in A? And the answer is yes, which is why, even though these things are technically equal, 1, 2, 3 is a subset of 1, 2, 3. And by similar logic, when we have the empty set, we need to look at that definition and say, is every single item that is in the empty set, is that also in this set? And because there's nothing in here, there's nothing to check. Therefore, yes, the empty set is a subset of every set. But another way to think about it, for every single element in the set, we have 2 options. Either we take it or we don't take it. So for example, in the subset where all we have is 1, what we're doing is we're taking 1, we're not taking 2, and we're not taking 3. In this one, we are taking 2, we are not taking 1, we are not taking 3. In this one, we are not taking 1, we are not taking 2, but we are taking 3. In this one, we are taking 1 and we are taking 2, but we are not taking 3. In this set down here, we are taking 1, we are taking 2, and we are taking 3. In the empty set, we are not taking any of them. So what it boils down to is that every single item in the set has 2 options. Either we take it or we don't take it, which means that we have 2 times 2 times 2 possible options. Or in other words, 2 to the 3. And this is still going to be true no matter how many items we have in our set A. If A is, 100, it's still going to be 2 to the 100 because we still have 100 elements and we're either going to be taking the element or we're not going to be taking it. So we know that this is true, but what we want to prove is that the cardinality of any finite set is different than the cardinality of a power set. And we can prove that it is different if we can prove that 2 to the cardinality of A is greater than the cardinality of A. Because if this side is greater than this side, then this side can't be equal to that side. Now what we want to do is a proof by induction, and the very first step whenever you do proof by induction is to prove the base case. And sometimes it'll be n is equal to 1 or n is equal to 0. In our case, we want to consider when n is equal to 0, and we want to consider when n is equal to 1. And note that the n here is simply going to be the size of the set, the cardinality of the set A. So all we need to prove is that this equation is true for the case of 0. So 2 to the 0 greater than 0. We can see that anything to the 0th power is going to be 1. That is greater than 0. And we have the case where n is equal to 1. So 2 to the 1 is greater than 1. So therefore, we've proven our base case is true for both of these numbers. The next thing we need to do is assume that the equation is true for k. Now k honestly is just an arbitrary number. You can think of it kind of like an instance of n. So if n is equal to 0, we can say that k is equal to 0. If n is 1, then k is equal to 1. They are basically interchangeable, don't let that throw you off. But what we're going to say is that 2 to the k is greater than k. And we are assuming that that is true. The next step to proof by induction is to prove that it's true for k plus 1. And the reason for that is that it's like having dominoes. If you can knock one over, then it will topple over and it'll hit the next one. And then that will topple over and hit the next one. So that relationship will continue to be true for all of the numbers from this point on out. Remember that k is some arbitrary number. We can say that k is equal to 1. We've proven that this is true, but we want to prove it for k plus 1. Or in other words, we want to prove it for 2 to the 2, because if we can do that, then we can prove it for 2 to the 3, and then we can prove it for 2 to the 4. If we can prove that it's always true, it's just toppling down and knocking over all these dominoes. So in order to prove it true for k plus 1, what we're going to do is we're going to write 2 to the k plus 1 is greater than k plus 1. If this is the case where k is equal to 1, then this would be our 2 to the 2 greater than 2. If k were equal to 2, then this would be our 2 to the 3 is greater than 3. If k were equal to 4, it would be 2 to the 5 greater than 5. Because again, remember, if k is equal to 4, that's the number that we plug in here and plug in here. So that's all it is basically an instance of n. But what we know is that 2 to the k plus 1 is the same thing as 2 times 2 to the k. Because all we're doing when we add 1 to the exponent is we're multiplying by another factor of that number. So in this case, that number is 2. We're just multiplying by another factor of 2. Or in other words, if we were to say that k is equal to 3 in this particular scenario, 2 to the 3 plus 1 is going to be 2 to the 4, which is equal to 2 times 2 times 2 times 2. But that is the same thing as saying 2 times 2 to the 3. Which again is going to give us 2 times 2 times 2 times 2. So that's all we're doing here is pulling out that factor of 2. And let me finish writing the relation here. We're saying that that is greater than k plus 1. Now let's go back to this line right here, and we're saying that 2 to the k is greater than k. Which means if we multiply both sides by 2, we still have the exact same equality, right? We're doing the same thing on the left side that we're doing on the right side, so that's not going to change anything about the relation. So we can say that we know 2 times 2 to the k, which is what we have here, is greater than 2 times k. So what we want to prove is that 2k is greater than or equal to k plus 1. And we know that this is going to be true for all values where k is greater than or equal to 1. And we could just plug it in. When k is equal to 1, we have 2 times 1. That's going to be 2 is greater than or equal to 1 plus 1, which is 2. So we have 2 is greater than or equal to 2. So as long as k is greater than or equal to 1, then this particular equation will hold. But again, going back to this line, we know that 2 times 2 to the k power is greater than 2 times k. So we can write that right here. 2 to the k power is greater than, for all k greater than or equal to 1. And we've already proven that this relation will hold for 2 to the 0 and 2 to the 1. So we have our base case here and our inductive step right here. We can say thus, the cardinality of the power set of A is greater than the cardinality of A.